Okay, last week I made a video going through a few examples of the trapezoidal rule and Simpsons rule and how to approximate them out. But some people emailed me and wanted the video going over the error estimates and how to actually calculate them. So here are the formulas. The error estimate for the trapezoidal rule: the absolute error is less than or equal to k times b minus a cubed over 12n squared, where the absolute value of the second derivative of f of x is less than or equal to k. And here, for Simpsons rule, the absolute bound on the error is less than or equal to k times b minus a to the fifth all over 188n to the fourth, where you take the fourth derivative of f and the absolute value of that is less than or equal to k. And on the one hand, you need to know the formulas, and to a certain extent, this is an online class, so I'm aware you can have these things next to you when you take the exam. But you also need to understand how you actually calculate these things out, and all things being equal, the biggest issue is generally finding a value for this k. So I have a couple of different integrals here that we're going to approximate, and we're not actually going to do the approximation using the rules. We're just going to find the bound on the error. And we'll start with this one right here. The integral from 0 to 2 of x cubed dx. And I know that n equals 4 for the purposes of this. My interval is 0 to 2, so I have my b minus a. Now we're going to find our absolute error. In order to do that, for the trapezoidal rule, we need the second derivative. For the Simpsons rule, we need the fourth derivative. So we can just find all of those. Right over here, we have f of x equals x cubed. So f prime of x is 3x squared. F double prime of x is 6x. The third derivative is just 6. And the fourth derivative is 0. So now I have my derivatives, and now the way this works is, for the trapezoidal rule, we say I have to find a k, the absolute value of the second derivative is less than or equal to k for all x's in the interval that I care about, in this case 0 to 2. So I look at my second derivative, 6x, and now I look at this interval. And on this interval, 6x, it's just a line and it's increasing. So I have to find its maximum value. And in this case, it's a line that's increasing. Its maximum value will occur at the right-hand endpoint, which in this case will be 2. So then the maximum value of this second derivative on this interval is going to be equal to 12. So then I know that, I don't need the absolute value here, 12 is less than or equal to k. So that's the k I can use. I can use any k I want. I could use 13 or 15 or you name it. But my goal is to have the least amount of error possible, so I want to make k as small as possible. And in this case, 12 will work. So then I would go up here, and I would say a bound on my absolute error is less than or equal to k, which we've established is 12, times b minus a, which is 2 minus 0, so 2, cubed, all over 12 times n, which for the purposes of this we said was 4, squared. And then I just solve that out, and then let's see. That's 12 over 12, 2 cubed is 8, 4 squared is 16, so 1/2. And essentially, with n equal to 4, which actually isn't that big of a deal, my approximation will be within 0.5 of the actual value using the trapezoidal rule, which, all things being equal, is not that bad. If I wanted to improve my estimate, I would increase the value of n, use more trapezoids, which would then make this bigger, because this would get bigger, so the square would get bigger, which would make the whole thing smaller, and my approximation would get better. One thing I will point out again using this, and we've done several other examples of these in the other videos. This is a line, and again, if I think about the line on that interval, at 0 I would get 0, at 2 I would get 12. So it looks like that. So my maximum value occurs there at the right, when x is 2 and I get 12. If I had some other graph, just for the sake of argument, suppose it looks something like this. If my derivative was some other weird polynomial or whatever, that's still a function, and if I need to find the maximum value of it to get k, I can just take the derivative, which in this case I already have. It's the third derivative, which is the derivative of the second derivative, and then just find the maximum value there using the first derivative test. So I can still apply the tricks I know from Calculus 1 here, but there are other tricks I can use, understanding, oh, this is just increasing, so I'll just pick the rightmost value. But there's lots of different tricks you can use to figure out that k. But then, keep my derivatives there. If I want to do the exact same thing for Simpson's rule, I use the fourth derivative. Here my fourth derivative is 0, which means for all x's I get 0, so I get 0 is less than or equal to k. Which just means that I can actually make k equal to 0. And then my error estimate for Simpson's rule, I said Simpsons and I wrote t. My error estimates for Simpsons will be 0 times b minus a, which is still 2 minus 0, to the fifth, all over 180, times n, which is 4, to the fourth. But of course here that's 0, so I just get 0. What this tells me is, if I use Simpson's rule to approximate this integral, I actually won't approximate it, I'll solve it out exactly. And I'm not going to take the time to run this through Simpson's rule, but if you want to check it, run this through Simpson's rule, see the value you get, then integrate this. We can all integrate this power rule pretty straightforward. See the value you get, and they should be the exact same. So in this case, we understand just looking at these, Simpson's rule should be an improvement on a trapezoidal rule, and I get that here. The trapezoidal rule gets me within 0.5. Simpson's rule actually makes it exact. But to see another one where we don't get something exact, we'll do the exact same idea, but now we'll use this. The integral from 0 to pi of sine x dx when n is equal to 6. So first off, if I want to find my error approximations, I need my derivatives. So let's see, f of x is sine x. So f prime of x, derivative of sine, is cos x. Second derivative, derivative of cosine, is negative sine x. Third derivative, derivative of negative sine, is negative cos x. Fourth derivative, derivative of negative cosine, is positive sine x. Now for the trapezoidal rule, I need to find my k. So the absolute value of the second derivative of x for all x's in my interval, in this case 0 to pi, has to be less than or equal to k. So I look at my second derivative, it's negative sine. The negative doesn't actually matter because we're looking at the absolute value. So it's sine of x on the interval 0 to pi. I could graph it. Well, let's see, 0 to pi. And again, I know it's negative, but we care about the absolute value, so I can just look at the positive sine x. Well, it looks like that. And here again, I can do different tricks on this, but I also understand how the sine function works. And I know the maximum for the sine function is always 1. Could I try to find a better value for k? Maybe if I had a smaller interval that I was integrating over? Maybe if I used more properties of the sine function. But in this case, on the interval 0 to pi, I get all values from 0 to 1 or 0 to negative 1, which means I know the maximum value for this will be 1, which then tells me this is 1. K has to be greater than or equal to 1, so I'll just let K equal 1. Now, I do the exact same thing, and we'll do it right here. K is equal to 1. I'm trying to leave all this stuff on the board as much as possible. So here, my error for the trapezoidal rule is less than or equal to K, which is 1, times B minus A, in this case pi minus 0, which is pi, cubed, all over 12 times n, which for the purposes of this, we went with 6 squared, which then gives me pi cubed all over 12 times 36, which is 432, I do believe. But we're just going to throw this into the calculator because the pi cubed is just not a fun thing. Assuming I can figure out how my calculator works. .0718, which means the bound of my error, 0.0718, which is not too bad. I mean, it's within 7/100ths, which is pretty close to the actual value. Now do the exact same thing for Simpson's rule. So for K, I find the exact same thing. I need the absolute value of f of the fourth of x, the fourth derivative on the interval, is less than or equal to K. Here my fourth derivative is sine x. But again, I understand on the interval 0 to pi, this is the sine function. Its maximum value will occur at 1. So then I can do the same thing here. 1 is less than or equal to K, which implies I can use K equal to 1. And again, I do actually stress here, there are a lot of values for K you can use. I can pick any value bigger than 1 that I want, but since my goal is to find the smallest possible error, I pick the smallest possible K value I can. That also means if I could algebraically show that maybe the maximum value of the fourth derivative of this function on that interval was 0.8, then I could use K equal to 0.8. But generally speaking, we don't have to go into that great depth to try to do that. We can use simple little tricks that we know. And again, in this case, it's a trig function. I know its maximum value is 1, so I go with that. And in particular, on that interval, I know it will achieve that maximum value, so I can just use that. If I had a smaller interval that didn't include where this sine function hits 1, then maybe I could try to algebraically find a smaller value for K. In this case, I just don't have to do that. But now, my error estimate for Simpsons. It's less than or equal to K, which is still 1, times B minus A, which is still pi, this time to the 5th, all over 180 times n, which for us is 6, to the 4th. And now I definitely hit buttons on my calculator. Pi raised to the 5th divided by 180 times 6 to the 4th. 0.0013. And again, here we see the error that I get for Simpsons will be a lot smaller than the error I get for the trapezoidal rule, which makes sense. This requires more work. It should be more exact. And according to this, just like we saw here, the bound of my error is much smaller. So that's a good thing. And again, I do stress, I understand from an exam perspective, it's an online exam. So there's a good bet, even if I tell you, don't have these formulas in front of you, you could have them in front of you because there's really no way I could check that. But the goal here is not necessarily to memorize the rules, it's to understand how to apply them and to say, okay, I want to approximate an integral, say this one. So I'm going to apply either Simpson's rule or the trapezoidal rule, do the calculation out and approximate the integral, and then I care about how exact is that approximation that I get. Okay, now I'm going to run it through the error estimate, correctly find my value of k, and then say, okay, now I have a rough bound on what the actual value of the integral is. So the point here is not necessarily the memorization of these rules, because there's lots of different approximations rules, there's lots of different Simpsons rules. The goal is to understand what's actually going on and to be able to interpret and understand what you're doing.